wait a minute here, Space Time General. I got you by inches. I got you by inches. I'm calling it. We're gonna put it in here. Make sure we got it first. I was putting up the photon yesterday. What you look like with the S&P and me readjusting. And just talking about that. Matter of fact, some math that help you do. I'm not saying I do. I'm saying it'll help you do. Okay. So home buyers, home builders, some numbers. These will help do certain things well. Sector analysis, X, Y, and Z, A, B, C, Feynman diagrams, about thesis diagrams, and other things. At any rate, inside here, ding, drill starts showing off about this police dog getting retired while you picking up some coyotes. I know, I am that coyote. I've been there, brother. I feel you. It's wild out here, giving everything in the universe. At any rate, Caesar Milan trying his best to train me in space-time ways. We're getting to it. Again, I got to get to the photons where I'm at. Yeah, I know, I'm built. You gotta... Well, this is about, again, overall numbers, crack cases on systems, about that'll get you in trouble. Even some Olympian got arrested in Russia not too long ago about thinning out the herd. The immortal herd inside of here about the Arkenstone, and some Bilbo Baggins being a barrel rider over here about who's doing what with what land while dealing with the triangulation of shorts, or trying to keep people on models of what wave functions they're doing before it shorts the shit out of everything. Food! You need to do food, because this guy right down here, he's going to be a board factory worker doing X, and you got to be able to do his X, right? That's going to be his numbers like he was a thing. I keep putting food and water and energy and gasoline into it. You figure you might want to figure it out. Got particles anyway. At any rate, inside here, we're digging to the photon. I have a good example. I know, right? Those could be. We could talk about those in a photon to certain Sydney and Sid. Skin your knee, your bicycle chain catches math problem, right? You know, those things. Because those things. At any rate, inside here, not having kindling mummy firewood in terms of Dems being able to do the job. Can we use him? Can we just do this? Please, honestly. What if I want to make money, government? What then? Well, how do you do that? I know we're building to it. I've been busy taking over hostages and stuff. A certain administration. You don't know you're my cow. What am I supposed to do? Walk up to you and be like, "Hey, move for me." Like, your name. Great conversation. We will start from there again against certain ideals and principles. Which methodology, whether that being the right or wrong answer, is the right or wrong answer. Again, some short goat path, run a cat or something, some other stuff, or psychologically JP, some Fed in the area of the tobacco farm or wherever, some God particle system, the physics engine of the how the thermodynamics problem. We are getting to that photon. We're summers around in here. Those. Man, I'll tell you. You gotta. Okay, so this is the spinal column of this thing here. Okay. That's 555 chip on the 888 T rookies. Dust a bunch of tardigrades. Get brothers take a step back. Okay, we're creeping up on it here, I think. 7 days. Got 7 days. I know, we're getting to it. We are getting to it. No, that's not what I want. Here we go. We're creeping into it. Well, we could use this in terms of the photon, because this is a portion of it. This is what I don't know about expansion yet. The moment of a train climbing a hill, going down a hill, given the momentum of the work, I could pretty much tell here I'm letting gravity do some stuff in the FMAs realistically. There's that up, down, standard model, Bromian algebra or something. And how that all clicks together in the clickety murder. Here we go. This is what I'm looking for here. Yeah, again, that's the known stata. Well, being the top right is this number right here, back to the positive form of the the solid state or gaseous state into, well, we're losing it, boys. This thing is negative. We got to go negative 273 Kelvin to make that solid state. Why that solid state is up here. Generally speaking, I don't know. The number is, can we get the energy off of the Epson's generator here for the photons we input to do the positive direction and the Penrose bits that we have to do to understand science. I know. Strip coulons, right, General? I got you frozen in time. The math test again. Some things that we do around here for what it is.
If we ever want to simulate a universe, we should probably start by learning how to simulate even a single atomic nucleus. But it's taken some of the most incredible ingenuity of the past century to figure even that out. So today, I get to tell you how to simulate a very, very small universe. Physics has been insanely successful at finding the underlying rules by which the universe operates. It helps that a lot of those rules seem to be mathematical. By writing down the laws of physics as equations, we can make predictions about how the universe should behave.
Okay, so look, I'm looking for a gradient on energy. Energy PE, big PE, and a billion over here for its market cap or whatever it is on a down cycle day. Across the NASDAQ being up and down and upside down pineapple cake factories, the doomslayers, little doomslayer around.
That's especially true when we study the quantum world, where the information density is obscenely high. As we saw in a previous episode, it takes as many bits as there are particles in the universe to store all the information in the wave function of a single large molecule. We also talked about the hack that lets us do that anyway. It's called density functional theory. DFT is good for simulating the electrons in an atom, but the behavior of electrons is comparatively baby stuff compared to the atomic nucleus.
Just the regular AR.
Every proton and neutron is
what is
composed
up, what is
of three
down?
quarks.
Well, that's a great question in the
like
first
gluons.
experiment of the
Well,
drill
actually,
teaches you
that's
what
a
up is, and you
simplification.
do it like that every time. The neutrino is that any way you did that without drill sergeant and then assembled that gun,
that just
there you
looks
go,
like
son.
three quarks from
And
the
those
outside.
two first parts,
the messy
that'd be the
interactions
receiver
of
and the
quarks
spring,
via
right?
gluons is described by quantum chromodynamics,
Ting.
or QCD. In the same
Now,
way
any
that quantum
configuration of
electrodynamics
yours, now
describes
we
the
do think,
interactions
alright, so I'm
of
going to change
electrons
the
and
fire
any
just
other
for
charged
funsies. I'm
particles
going to put the
via
firing pin over here on
photons.
a Wednesday because
We're going to come back to a full description of QCD very soon,
together, yeah.
but you don't need it for this video. Today, we
Stuff
just need
that
to
made the
understand
Milky Way.
why it's complicated.
Hawking Harry black
Instead
hole
of
problem
the one
and
type of
void
charge in QED, in QCD there are
to
three,
collapse
which we call
that
color
to
charges,
then
hence
why
the
would that number be different?
chromodynamics.
It's like
Also,
ROTC,
quarks never
go
appear on
out,
their own.
study
They're always
hydroxide,
bound to
got
other
it.
quarks in
Go out,
composite
study the
particles called
S&P, go
hadrons,
to the market
of which
Wall Street,
protons and neutrons
figure
are
out
an
the
example.
Bluestone Militia,
To test
CT
QED,
paradox on the
we
dry
can
wet
chuck
line
a
of a
photon at an
Bluestone.
electron and see what happens.
So what's that actually
But
mean?
to
That's
test
a trick
QCD,
question. You'd have to
we
ask the
can't
boss,
just poke a
like
quark
you
with
would in
a
the
gluon.
mill, about
Instead,
what
we need to
comes
figure
next,
out
and I would tell
what
you
the
that
theory
place
predicts
is
about
actually
the properties
a
of
math
hadrons
thesis for
that are actually measurable.
You have to get some
And
training
that's near
at that
impossible
place, sign in
because of
for a week
a
or
third
two
problem.
while they do some drill and you do
force
some free
mediated
labor
by
for them to
gluons
figure out
is very strong,
manufacturing,
earning it the
right?
name
It's
the
the
strong
pitch roll
force.
and yaw, your
And
torch,
that strength
how wet the torch
turns
is,
the
you
interior
clean
of the
rock, the
hadron
whole
into a
process, 'cause
maelstrom of
that's gonna zero
activity
that thing
which
out.
can't possibly be
Then on the
calculated on a
rails, the
blackboard.
units by this,
And
they
at
get a
first
little
glance looks
squishy,
impossible
more
to
blocks,
simulate
less
on any
blocks,
computer
how the
we
cutoff
could ever
works.
build. Or would be if it
Maxwell
weren't for the
Lehman.
fact that people are exceptionally clever and they came up with lattice
everywhere, like
simulations. Now, before we do the hard
I never
stuff,
was a mechanic,
let's
but
review
there he
the
was, and now I had to
comparatively
help hold the
easy
thing. I was
quantum
a mechanic.
electrodynamics. Say we want to predict what happens when two electrons are shot towards each other. We can actually
Well, it could stay
calculate
in the
the
mill.
almost
We do
exact
have the other
probability
kid.
of them bouncing
They can
apart
do it
at a
without
given
me.
speed and
It
angle.
might be a little hard.
We do that by adding up all the possible ways that
break off.
interaction
Like a
could
normal
happen.
day,
For example, there are various
I'm willing to
ways that
take
the
on
first
one or two
electron could
things.
emit a virtual photon which is absorbed by the second electron, or vice versa. Or it could happen via two virtual photons or more, or one of
Put that on
those
your hand,
photons
right?
could
You know, then you gotta
spontaneously
squint
form
your
a
hand, like
virtual
paint a big ring
electron-positron
on your hand,
pair
and your hand squished,
before
and
becoming
you
a
did
photon
TikTok
again,
about
and
it.
so on. Each family of interaction types is represented by a Feynman diagram, and quantum electrodynamics gives us a recipe book
Okay.
for adding up the
So pause. Time out. This is you. And I know what you're thinking. Well, that's not what you means mathematically. Shut the fuck up. This is you. This is you doing a Feynman diagram on X. Now, why is that special? Because these numbers are not any S&P or graphic output of a Brothers Truth table across the technique of how you stonecutters that system inside of there to block A to block B in M1 to M2, F1 plus F2, no matter what real math would come in there for you at the one integer. I am not 0, X, I am S and P, again, any of those numbers that I said are irrationally in energy. If I do believe that this is gamma, or some radiation background, some dot metrics that's not temperature, it's more photons, more in a quantum space of this nature, and that's to the power of what I do believe is nu or mu, so that's going to be a squared platform of it's going to divide. It's going to say that at that point in time it's a fair place to say the division. It could go up or down in there in terms of the probability of some Heisenberg stuff. And that's back to you being that Heisenberg from it started this using the chemistry experiment, figuring out cellophane is some numbers that then you have to figure out on. Well, that's the amounts and proportions instead of doing the entirety of the Jacobian matrix of elements and combinations that would actually function out some kind of system. And go figure that when you get to that point, it'd be at that derivative of high and low inside of those states of minus some irrational u that was a negative number in form of determining the timeline that you said those systems were for. Now, that'll get into some of the philosophy of why math is a fist fight against some of the ideas of combatives and combinations. High probability goes to a bit of FMA to right-hand rule.
Probabilities. We talked about this stuff in some previous videos, but there are literally infinite ways this interaction could happen.
Do we have any
each
bases
more
on
complex
Mars?
than the last.
Until we get
So,
there.
how do you know when to stop adding up your Feynman diagrams? Well, we kind of got lucky with that in the case of QED. As the interactions get more complicated, their probabilities get smaller and smaller. Diagrams with more than a few twists
Mercury,
and turns add almost
Venus,
nothing to the
Earth,
probability. So we only have to include the
Mars,
simplest few levels.
Jupiter,
Each
Saturn.
pair of vertices on a Feynman diagram represents the probability of a pair of electrons interacting
Black
with the
hole,
electromagnetic field,
different
emitting and
ranges of
absorbing
stars,
a virtual photon.
cleansing the
And there's a set probability
highs
of that
and
happening
lows,
each
EM
time.
fields
It's
on
around
different ranges
1 over
of spin
137.
of black hole,
So every
mass
time you
of
add
black
another pair of
hole.
vertices to a Feynman diagram, the interaction it represents becomes 137 times less likely. A diagram with only
Think
6
about the goat
vertices
in the
is
car
nearly 20,000
experiment.
times
When
less
you have
likely
three
than the
doors,
simplest
it's
two
pretty hard
vertex
choice
diagram.
to say, well,
So
choose
we
this
just
one,
choose the
and then
precision
you
we
still
want
only
for our
have 50
calculation
choice,
and
when
ignore any
you will
interactions
always
that
choose
nudge the
first order
probability by
mathematically,
less than
and
that
you
precision. This
probability
1 over 137 thing
makes
is the
things a lot
fine
easier.
structure
Probability
constant.
finding
It's
the
the
car
coupling
becomes
strength
way
between the
higher because
electron and the
being the
electromagnetic
first
field.
door that it
The
is
smallness of the fine
is
structure
very
constant
mathematically
means
odd
the
to
electromagnetic
being
interaction
where it
is
is, as
relatively
long as
weak,
I always gravity
relative
that spot.
to the
It's
strong
alpha.
force anyway.
We always
Okay,
use that
back to the strong
technique.
force.
The math will
Now,
continue.
let's say we have two quarks hurtling towards each other. They're going to interact by the strong force, which is mediated via virtual gluons of the gluon field rather than virtual photons of the electromagnetic field. We can draw Feynman diagrams of these interactions, now with cute curly gluon lines. Presumably, then, to calculate the probability of a given interaction, we again just add up diagrams, with the probability of each diagram determined by the number of vertices. The coupling strength for the strong nuclear force is ingeniously named the strong coupling constant. It is much higher than the fine structure constant, and it's of order 1, although it depends on the energy scale. That's what makes the strong force strong, and it's also what makes the strong force interactions very difficult to calculate.
How much was that physics?
You no longer have the luxury of throwing away all but the simplest Feynman diagrams when you're calculating the interaction probability for your pair of quarks. Adding new vertices doesn't decrease the probability anywhere near as quickly as with QED. This means you can't possibly do this calculation with pen and paper. In fact, it's extremely challenging to do QCD with the Feynman diagram approach, even with computers. Now, before any particle physicists start shouting at me, I'll quickly add the caveat that there are some unusual cases where the strong coupling constant can become small and quarks can be understood with Feynman diagrams. And this is the phenomenon known as asymptotic freedom, but if I tried to explain that too, we would be here all day. In general, if we can't calculate what quantum chromodynamics predicts for the behavior of quarks, then how can we even test the theory? Well, we need to abandon Feynman diagrams. In fact, we need to abandon the idea of particles altogether. See, it turns out that the virtual particles that we were using to calculate particle interactions don't actually exist.
Remember the math on this?
Now, we've talked about that fact recently. Real particles are sustained oscillations in a quantum field that have real energy and consistent properties. Virtual particles are just a handy calculation tool, a way of representing something deeper. They represent the transient disturbances in quantum fields due to the presence of real particles that couple to those fields. The coupling between quark and gluon fields is so intense that the disturbances of those fields are way too tumultuous to be easily approximated by virtual particles. Instead, we have to try to model the field more directly, and that's where lattice QCD comes in. It's an effort to model how the quantum fields themselves evolve over the course of a strong force interaction.
Diagrams on the spectrum,
similar to how Feynman diagrams work. To do this, you need to account for all possible paths between the starting and final field configuration to get the probability of that transition happening. Now, there's a good reason we don't do this for electromagnetism. There's an astronomical number of configurations that the field could pass through in the intervening time. No supercomputer could do that even given the entire life of the universe. For QED, Feynman diagrams let us reduce the number of field configurations by approximating them as virtual particles. But for QCD, we have to stick with fields, and so we need a different hack. In fact, we need a few of them. Let's make sure we understand exactly what we're trying to do. We want the probability that some wiggly quantum field wiggles between one state and another. Let's go back to electromagnetism just for a second because there's an analogous case here